Welcome back. So let us continue the discussion on this horizontal axis, their momentum theory. So what we have talked about momentum theory, one-dimensional momentum theory with weak rotation, beam theory, and what we have established the criteria for maximum power coefficient, maximum thrust coefficients, and some of the design consideration of the code or the solidarity and all these things. An important aspect which has kind of come out of that discussion is that uh, uh, how one can have this design of the blades, but obviously at the different section of the turbine blades or the rotor blade, you will have different section of the profiles, and those airfoils are going to be different because the twist, solidarity, all these are at different locations are different. These things are more going to be more important or clear when we'll be talking about the dynamics part of it. So each segment of the rotor blade, how they contribute to the overall system dynamics or the rotor blade dynamics. And when you talk about those dynamic or that aspect of it, so that also kind of lead to the design. So what we are trying to do here is that see the wind energy of the wind, which is kind of coming to this particular what do you call on the um, blades or the rotor blades, then the rotor due to this lift and it rotates, and the main shaft which is connected with the gearbox that transmit that to the high speed shaft, and then there the generator is connected which is converting that to electricity. So that's the overall mechanism of these things, but this is what is going to coming to that aerodynamics design and all this. So having said that, the important aspect of it is looking at some of this nomenclature of airfoils and things like that. So that is what we are going to talk about here. So airfoils, which are well-known streamline structure, okay. So which is known for uh, so this used for generating lift force. Usually defined, the lift force is defined the perpendicular to the direction of the oncoming airflow, and the lift force is we'll see that mm, so there are it can use in the blades, wings. So if you see this particular airfoil, this is called leading edge, this is trailing edge, then you have the line which is connecting the leading and trailing edge called the chord line, or that's what the chord length is. And the one which is dividing the airfoil into equal segment called the camber, and in between you have the thickness. So that's the typical airfoil nomenclature uh, that you have. Okay, so what is there is now, if we look at, so these are all kind of an cambered airfoil. Okay, these are called cambered airfoil. If you see here in this picture, you have leading edge, trailing edge, then chord length, you have a lower camber. So the chord which is connecting between the leading edge and trailing edge, that divides the thickness into two segments. One is called the upper camber, this is the lower camber. So camber is the asymmetry between the two acting surfaces of the airfoil. The airfoil which doesn't have camber called the symmetric airfoil. The benefits of cambering or long back, which is 19th century discovered. And now the airfoil can be positive cambered. If the upper surface is more convex, the airfoil could be And the camber is complex property that is can be more fully characterized by the camber line, and then one can define the thickness at different location of the airfoil in this direction, which kind of describes the thickness of airfoils at any given point. So the upper point you can, let's say, this, and the lower point. So this is the camber line curve, the z with function of x, and the thickness by 2. So this is how the upper and lower point one can be estimated. Now there are different kind of airfoils which are used. So there are some conventional airfoils. So if you see, this is used for high lift producing devices. So it is used wherever you would like to produce high lift. This is more like a general purpose airfoil. These are again high speed airfoil. That means these are used in some vehicle or aircraft or somewhere where you are encountering high speed. Again, this airfoil, if you see, this is a zero camber. This is upper surface is more convex. This is negative camber because the lower surface having more convex. So the camber curvature usually dictates the positive or negative camber and things like that. Now, conventional airfoils, if you see this particular airfoil, it has some property. It's low camber, low drag, high speed, thin wing section suitable for race planes, fighter, interceptors. Okay. You have very deep camber. This is used for high lift, but at the low speed operating condition. Thick wing section suitable for transport, fighter, bombers, and all this. Okay. Similarly, you have deep camber, which is used for high lift and low speed. Thin wing section suitable as above. This is for low lift high drag system. The reflex trailing edge with section, very little movement of center of pressure, good stability. This is symmetrical wing section, pretty much similar to the above. This is a thicker for better structure and lower weight. Good stall characteristics. This airfoil camber is maintained further rear rod, which increases lifting capacity over more airfoil and decreases drag. So this is what you can have when you have different kind of airfoils provide different nomenclature and different advantage, disadvantage, and their uses. So obviously these are all based on the use of the airfoil, what kind of airfoil one would like to choose, and that sort of dictates the um, now when you talk about the nomenclature of the airfoil, this was given by the NACA, which was National Advisory Committee of Aeronautics. And it defines airfoil shapes and also aircraft wing. And that's what the series are most of the time. This airfoil which are used, they are called in the namingly NACA series. And there are few, nomenclature has certain aspect of it. So here, if you see, the one is the zero lift line, two leading edge, three nose circle, four maximum thickness, five camber, six upper surface, seven trailing edge, eight camber mill, nine lower surface. So if you kind of remember this, then how we define these things, the other things like NACA initially developed the number the airfoil system. So what happened is that during 1920 and into 30s, the NACA developed the series, thoroughly tested airfoils and devised a numerical designation of each airfoil. So they had 4-digit series, they have 5-digit series, they have 6-digit series. So that's how the digit came up. 1929, Langley had developed this system to point where the numbering system was complemented by an airfoil cross-section. And the complete catalog of 78 airfoils appeared in NACA annual report of 1933. So engineers could quickly see the particularities of airfoil shape and the numerical designator. For example, NACA 2415, it specified camber lines, maximum thickness, things like that. Obviously, this provides that when you try to design the system, you know what kind of airfoil you would like to use and also what would be the nomenclature. Let's start with the 4-digit series. So the first digit here, that is 2, describe the maximum camber as a percentage of chord. So this 2 is the 2%, maximum camber of 2%. Second digit describes the distance of maximum camber from the airfoil leading edge to in tenths of chord. So here the 4 is that the maximum camber located at 40% or 0.4 of chords from the leading edge. And last 2 digit defines the thickness with a maximum thickness of 12%. Similarly, so this is 2412, this is probably 0015. 00 stands for, this is a symmetrical aerofoil. So that means there is no camber. So there is no point of maximum camber. Only thing that you get the thickness ratio. So you get only the, so as soon as somebody sees this 00 series, immediately you would be able to identify that this is a thickness which is there. Then you have 5-digit series. So the 5-digit series kind of the format is LPSTT. L is single digit which representing the theoretical optimum lift coefficient and ideal angle of attack, which is the 1.5 times of the L. P a single digit for x coordinate of the point of maximum camber, so maximum camber at 0.05 P. S a single digit number which talks about whether it's a simple camber or reflex camber. AT again the maximum thickness in percentage of chord, like what you have in 4-digit series. For example, 23112, the lift coefficient is 0.3 because 0.515 into 2. The point of maximum camber is 15% of the chord, so 5 into 3. Okay. Reflex camber 1 and 12 is the thickness. Okay. So that's what you have in 5-digit. Similarly, you can have 6-digit series. So those series are, so every series has this kind of nomenclature. Now, talking about the aerodynamic forces. So the aerodynamic force is generated when the blade actually rotates through the air. So the lift and drag act through the center of pressure, which is average location of the aerodynamic forces on an object. These are mechanical forces and they are generated due to the interaction of the blade with the, or contact of the blade with the air. So lift force, which is kind of a defined perpendicular to the direction of the oncoming airflow. And this is a consequence of the unsequential pressure difference across the upper and lower surface of the airfoil. And drag force is usually, and this is due to both interaction and so these are some. Then you have pitching moment and all these things. So which so the lift generation is kind of what we get using the fundamental principle of Newton's first law of motion and second law of motion. So it's then third law of motion, which says so Bernoulli's principle also increasing the speed of the fluid simultaneously. So these we have. What it says, the Newton's second law, the force causes a change in velocity with in turn generates another force. So when the flow passes by the airfoil, there is a pressure difference. So that's what. So if you see this air coming and this is the kite, so the resultant portion allow the kites to go up. Same thing happens with the wing. So there is air coming, the wing having this pressure difference, and this generates then down it downward. Now, obviously, when there is a pressure difference, it is obvious of the geometry. Important when you have a higher turning, that is in this case, you get a use for stability and control of the. Now we can see a volume where air expanded, so you have a high. So because of that, you get so increase airflow, decreases in pressure. So the air flowing over the curved upper surface of the wing speeds up. What happens when the airflow comes and the flow moving less pressure, reason which is going to contribute towards the effect. So increase in speed reduces pressure above and wing and produces that. So how does an airfoil produces an lift? So if you see, this is a typical flat plate, or here we see the airfoil. So the flow velocity over top of the airfoil is faster than on the bottom surface. So you can have some kind of a steam tube, let's say A, senses upper portion of the airfoil as an obstruction, and steam tube A is close to smaller cross-section area, whether in the lower surface, steam tube B is a higher cross-section area, so the flow expands, slows down, so the pressure builds up there. So that's how you get this kind of an pressure difference over the airfoil surface. And this pressure distribution, you can see that generates this lift force, which is normal to the system. So this is how it generates. Now you have relative wind effect on flight. Okay, flight relative wind has both a speed and direction. Okay, so when a plane flies, relative wind blows in nearly an exact opposite direction. So this is what the relative wind, because the airfoil having an angle of attack. So this is what is going to have a relative wind. Now, angle of attack plays an important role also, not only for airplane. We can see the example of airplane, but here is an example of the airplane. If a plane alters its pitch, which you can see here, okay, the up and down movement of the plane nose, the angle of attack on the wings will increase. Okay. So when the angle of attack increases, the blade produces more lifting force. So there is a typical CL versus angle of attack curve for general aerofoil. So with the increasing angle of attack, you can see the CL is increasing up to a certain angle of attack. So this is a point where what happens is that if your angle of attack is too much, then flows tend to separate. And once flow tend to separate, then you have a lot of loose speed zone and all these things. There would be more viscous effect, which is going to be dominant. So it increases the drag. So that is why beyond a point, actually, where it stalls and the CL starts dropping, and that can be easily visible here. So point at which plane stalls around 15 degree, because these are standard airfoil, but this is not something. So what you can see when you are at the lower alpha or angle of attack, the flow remains attached so nicely. You can get leap, you have drag. But as soon as you increase the angle of attack, you see the flow like that. So this is the separated flow region. So more and more you have separated flow region, obviously your lift decreases because lift is primarily uh, delta P between the upper surface and the lower surface. But here this is going to be a problem. When separation occurs, you have adverse pressure gradient, not favorable pressure gradient. So lift actually, in this case, lift actually starts decreasing. So what happens is that, so this lift and drag are primary forces that act on the aerodynamic body. Okay. This is a measure of usefulness of the device. Drag is the force which retards the motion. So basically, even for your rotor blade, the drag force is going to increase your losses. Power production is going to be less. So one has to understand the relationship between lift and drag. And with fundamental relationship is developed relating force and aerodynamic coefficients. Then you can. So if you look at those things, you have lift coefficient. So this is a lift force divided by area into dynamic head, drag coefficient, pitching moment coefficient. So these are fundamental um, aerodynamic coefficient. Then one needs to have for design and things like that. Now, what creates these aerodynamic forces? So aerodynamic forces are exerted by airflow and come only two sources. One is pressure, that is how this gets distributed over surface. So this is acts normal to the surface, then shear stress, friction on surface, which acts tangentially on the surface. Net unbalance in the force creates the aerodynamic force. No matter how complex the flow field, no matter how complex the shape of the body, the only way nature has of communicating an aerodynamics force to a solid object or surface is through the pressure and shear stress distribution that exists on the surface. So now you can see how the relative to the, so this is an airfoil which has an angle of attack alpha. So this is the relative wind and this is the component of the forces. Okay. So total resultant force is R, and you have two component. One is lift component, which is perpendicular, and drag component, which is parallel to the system. And then aerodynamic moment. So the total lift force on airfoil is summation of F1 and F2. Lift is obtained when F2 is greater than F1. Misalignment of F1 and F2 creates the moment, which tend to rotate the airfoil or wheel. Value of induced moment depends on the point about which moments are taken. Moments of the leading edge, a quarter quad in general, this is MC by 4 where it acts. Now, what is there? You have this variation of the lift force, drag force, and moment with alpha. So lift drag moment on an aerofoil or wing will change as alpha changes. Variation of these quantities are some of the most important information that airfoil designer. So one is the aerodynamic center point about which moment essentially do not vary with alpha. That's called MAC, constant independent of alpha flow. Low speed airfoils aerodynamic center is nearly quarter quad quad. So this is nearly C by 4. But yes, it depends also the airfoil. So how one would find the lift coefficient? So you get the pressure distribution over this airfoil surface. This is along the chord. The pressure coefficient would be the PL minus P naught by rho V square by 2. Cp is the difference between the local pressure between lower and upper surface. So the area between the upper and lower surface distribution is proportional to the lift. And once you find the lift, then you can find out the lift coefficient, which is Cp. So now one can find out the lift on a blade. So this is a typical aerofoil, and this is leading edge, this is trailing edge. So this would be finite length in this side. So there is a finite aspect ratio. So this is small infinitesimal strip, and the angle is given. So the lift per unit span is something very important. So lift, that is due to the pressure differences, all this that you get. So one can find out by integrating lift force between leading edge to trailing edge and the component of these forces. So one is PL cos theta minus PU cos theta of ds. ds is this small segment here. So you go from leading edge to trailing edge. So ds cos theta is dx. So one can convert this to 0 to c PL dx minus PU dx. Lift per unit span. So adding and subtracting P infinity. So there is some kind of an algebraic manipulation that one can do. And what you can do is that 0 to C PL minus P infinity. So PU minus P infinity dx. So now our definition of lift coefficient is L by Q infinity S, where Q infinity is half rho U infinity square. Then we write L by Q infinity into C because it's an unit span. So combining these two quantities, so what we get CL is 1 by C 0 to C P1 minus P infinity P lower and P upper minus. So CPL, this is the lower surface coefficient, this is upper surface coefficient. So what you get CL as an 1 by C CPL minus difference of the upper and lower surface coefficients and this thing. So if you look at the lift coefficient versus angle of attack, you have zero lift angle of attack, which is alpha 0. The slope of the linear region gives the infinite wing lift coefficient. The reference lift coefficient is given in the point 0. So this is the case where flow remains attached, and this is where the flow gets separated. So that is where it goes to the stalling point of the system and things like that. So lift is not pushing force, it makes the rotor to rotate. So this is where when you talk about the context of the turbine blade. Okay. So when you talk about the context of the turbine blade, so as we said, the blade rotates. So obviously every section there are airfoils and they are having angle of attack. So due to this wind and the relative pressure difference, the lift force, this force allows this to rotate. Okay. So obviously the commonality is that you get lift and drag. So you try to minimize the drag for the account for the losses and things like that. So if you try to make a connectivity of this blade, so this is your center point and this is how the blade goes. So this is your tip. This is at the root close to the hub. And this is how the radius varies and this is where the rotation is. Now this particular segment, if you look at it, this is having an airfoil section and this is the wind speed. Now that airfoil, if we take it separately and try to, basically it's a zoomed in view and this is the wind speed. So what happens, this is coming to the airfoil, and airfoil having an angle of attack of alpha, there is a twist of beta, and this is the flow angle. So you get lift in this direction, you get drag in this direction, then you have all these component L sine phi, D cos phi, and the W, which is the relative wind speed. So these are the calculation that we have already seen, that taking an airfoil and taking these angles and their concept and finding out the rest of the component. So if I summarize that, so the pressure difference across the airfoil surface that actually generates the leak coefficient. So you can always find out by doing the integration pressure across this. One can represent in different ways like lower surface lift coefficient, upper surface lift coefficient, and that way. But if you increase the angle of attack, one point of time there could be flow separation. So more and more self flow separation happens. So there is a drop in the lift. Obviously, drag increases. Okay. So this is the same concept which needs to be used while designing the rotor blade also, because the rotor blade, the lift causes it to rotate, and the rotation is the main component here where you are converting your wind energy. So the wind flow hitting the rotor blade, because of their airfoil sections at different planes and different things, it rotates. That rotation goes to the low speed shaft to high speed shaft to generator and produces the electricity. Okay. So we'll stop here. We'll continue the discussion on wick and all this thing in the next session.